Dear students, today we'll start the discussion of Module 2 from this operating systems. So this Module 2 consists of again 3 chapters. So in that today we'll start chapter number 4, that is multi-threaded programming. So these are the contents that we cover from this chapter. That is, we start with overview, multi-threading models, thread libraries, and threading issues. So let us start the discussion with the overview of the thread. So what is thread? So basically a thread is a basic unit of CPU utilization. So it shares with other with other threads belonging to the same processes its code section, data section, and other operating system resources such as open files and signals. So what exactly the thread is? So we know that whenever you start executing a program, a process will be created. So whatever the activities you carry out, so all will be confined to that corresponding process. You consider the example of typing a Word document. So you have opened Microsoft Word, and in that you are typing content. So whenever you are typing, at the same time, you may expect that it should automatically do the spell check. It should automatically do the saving, that is auto save, and so on. But it is not possible for a single process. So that's why here what it does is, so far in that process it is going to create the number of threads, and each thread will do a subtask of that. Like this for spell checking, one thread will be running. Okay, for auto save option, one thread will be running. For auto complete, one thread will be running, and so on. Okay, so in this way the threads can be used. So here we have the two types of processes, that is the single and multi-threaded processes. So by default, every process will have a single thread of execution. So every process will be usually a single threaded process. So we know that whenever we have a process, the process will be having its code segment, data segment, and associated files. Along with that, it will be having the registers and the stack. So here we have a single process. So here whatever the data structures that this process is having, so all are shared by this thread, because we have only one thread here. Here another figure we have the process, that is multi-threaded process. As the name itself indicates, multi-threaded process means in the same process, in the single process is having the number of threads. Okay. So in this case, what happens? We know that whenever we create a thread for the process, the thread will share its data segment, code segment, and other resources. Here it is very clear. So here in this example, we have taken 3 threads that are created for this single process. So this thread is having its own registers and stack. This thread is having its own registers and stack. This thread is having its own register and stack. But whatever the code segment, data segments, and files that are associated with this process, so these are shared among all the different threads. Because we know that whatever the particular segments, already we have seen what are the contents of this code segment, data segment, and the corresponding files. So here you cannot create the copies of these for every thread, but you have to create the copies of stack and register, because we know that stack contains the temporary data that will be generated during the execution. Here every thread is having a separate task. So that's why whatever the data that is generated by each thread, to store this, we have the separate stack. And the same thing is true for the registers also. Okay. So next we'll see the benefits of multi-threading. So there are mainly 4 benefits we have listed here. That is responsiveness, resource sharing, economy, and utilization of multiprocessor architecture. So what is responsiveness? We know that when a process is executing, it may create the number of threads. If you don't create the number of threads, what happens? When a process is executing, okay, so in between, if the process executes the blocking system call. So in that case, that entire system, that entire process execution will be halt. Okay, but here if you have the number of threads, so what happens is the number of threads are running. In that, if any one thread executes the blocking system call, so only that thread will be threads execution will be halted. It will not affect the execution of other threads. So as a result, you will continue to get the response from the execution of this particular task by the thread. So this is nothing but the response. Second one is a resource sharing. We know that whenever we want to perform the different tasks, so for every task you can create a new process, and we know that whenever a new process is created, it will be having its own copies of the resources. Okay, but here for every task, if you go on creating a new process, so it is going to incur the performance loss. Okay, so that's why here, in order to avoid or in order to overcome this problem, you can have the option of resource sharing by creating the threads instead of creating the processes, because we know that whenever you create the number of threads for a process, so whatever the resources that the process is having, the same are shared among all the threads. This is resource sharing. The third one is economy. The same thing, whatever the discussion we had, because if you go on creating the number of processes for every process, you have to allocate the different segments, that is data structures. But if you create the number of threads, it is not required. It will increase the uh, resource sharing. So in turn, it will reduce the economy. It will become the economical one. So last one is the utilization of multiprocessor architecture. So that's what a multiprocessor architecture means. The number of tasks will be executing at the same time. So it is possible through the multi-threaded approach. So these are the four benefits of the multi-threading approach. After this, we have the discussion of user thread. So we know that your operating system will be running in two modes, that is user mode and kernel mode. So that's why again the threads will also be categorized into two types, that is user threads and kernel threads. So user thread means the thread management done by the user level thread library. So here it will be in the user space only. So the three primary thread libraries that comes under that are the examples of user threads are the POSIX Pthreads, Win32 threads, and Java threads. Next one, we have the kernel threads. As the name itself indicates, these are the threads that are supported by the kernel, and these will run in the kernel space. The examples of the kernel threads include the means the systems that support this one include the Windows XP or 2000, Solaris, Linux 264, Unix, and Mac OS X. In next we'll see the multi-threading models. So in order to understand how exactly the multi-threading approaches are handled and these are used, we have the different models here. So here we have the three models, that is many-to-one, one-to-one, and many-to-many. We'll discuss this one by one in detail. So let us start the discussion with many-to-one model. So in many-to-one model, so here the many-to-one means this is just a mapping of the user threads and the kernel thread. So first many means we have many user threads that are mapping to the single kernel thread. So here in this case what happened? So here the many-to-one means the many user level threads will be mapped to a single kernel thread. So the examples of this are the Solaris green threads and GNU portable thread. So here that is shown here by this particular figure. So you can see we have the number of threads, user threads, that are mapping to a single kernel thread. So here what happened? So we know that although you have the number of user threads that are mapping to a particular kernel thread, at that time only one user thread will be allowed to interact with kernel. So in this case, the other threads will simply waste their resources and time. Okay, and here one more thing is, whenever a particular means here whenever one user is executing a task, the other cannot execute its task, because at a time only one user thread can access the corresponding kernel thread. So this is about the many-to-one model. So to overcome that drawbacks of many-to-one model, we have one-to-one model, means for every user thread we have the corresponding kernel thread. Okay, so here For every user thread we have corresponding kernel thread means, so whatever the drawback of the many-to-one model was there, that is at a time only one user thread will be active and it will be allowed to execute. So here the parallel execution is not possible, but in case of one-to-one, so it is possible, because here every kernel thread is having the associated every user thread is having the associated kernel thread. So that's why the one-to-one mapping is there, and every user thread is allowed to execute parallelly because it is having its corresponding kernel thread. Okay, so the examples of this are XP 2000, Linux, and Solaris 9 and later. So it can be shown diagrammatically in this way. So what are the drawbacks of this? Here the drawback is, for every user thread the kernel thread should be created. This is the first drawback. And when the number of threads is going to increase, so it is going to increase, it is going to decrease the performance, it is going to increase the system load. Okay, so this is about the one-to-one model. So next one we have many-to-many model. As the name itself indicates, the number of user threads are mapped to the number of kernel threads, but the number of kernel threads should be either less than or equal to the number of user threads here. Okay, so here it allows many user threads to be mapped to many kernel threads. So allows operating system to create a sufficient number of kernel threads, and Solaris prior to 9 and Windows NT 2000 with thread fiber package will support this particular model. So the same thing is shown here. So we have the 3 kernel threads here and 4 user threads. So we have many user threads mapped to many kernel threads. So here again the number of user threads will be allowed to execute parallelly, uh, because every user thread will be having the corresponding kernel thread. And here, as you are going to restrict the number of kernel threads to be equal to or less than the number of user threads, the performance bottleneck is reduced compared to the previous model. So next one we have the two-level model. So you can consider this as a hybrid model, which is the combination of many-to-many and one-to-one. So it is as a given, it is similar to M is to M, except that it allows a user thread to be bound to the kernel thread. So the example machines which supports this model are IRIX, HP UX, True 64 Unix, and Solaris 8 earlier. So the same thing is shown diagrammatically in this way. So here we have the two-level means it is the combination of many-to-many as well as the one-to-one. Okay, so here if you want to have a single means the independent user and the kernel thread, you can go with this, and if you are good with this, so you can consider this also. So you can consider this as a hybrid model. So after this we have the discussion of the thread libraries. So this thread library means what? So the thread libraries provides a programmer with the APIs for creating and managing threads. Because we know that for creating and executing the process, we have this system called like fork and exec in Unix. In the same way, in order to deal with the threads, we have the thread libraries, and to use those thread libraries, your system is going to provide the APIs. So through these APIs, it is possible to create and manage the threads. So there are two primary ways of implementing these thread libraries. The first one is library entirely in user space, and second one is the kernel level library supported by the operating system. So the pthread, so it may be provided either as a user level or the kernel level. So the POSIX standard API for thread creation and synchronization. The API specifies behavior of the thread library. Implementation is up to the development of the library, and common in Unix operating systems as well as Linux and Mac OS. So here we have the Java threads. So Java threads are managed by the JVM, that is Java Virtual Machine. The Java threads may be created by implementing the runnable interface as follows. So I think you might have already studied Java. So here you can the Java provides an interface that is runnable. So if you implement this runnable interface, it is having a particular abstract method, that is public abstract void run. So by implementing this interface, you can implement the Java threads. So here again we have the Java thread states. So here we have the different threads that are shown along with the different operations or the functions which will cause the transition from one thread to the another thread. So you can see the first one we have new. So after that we have runnable. So during the runnable, it may move to the either blocked waiting or timed waiting, and at the end, it will move to the terminated. Okay. So time. So this is about the Java thread states. Next, we have an example implementation of Pthreads. So here we have the producer consumer solution using Java thread. The code is here. So we have to import java.util.date. So after that, we have the public class factory. So public static void string. So first to create the message queue. It is channel date queue equal to new message queue of date. So after that, here they create the producer and consumer threads and pass each thread a reference to the message queue object. So the constructors are called, the objects are created. After that, the producer dot start and consumer dot start to start the threads. After this, here we have implemented the runnable interface. So the class producer implements the runnable interface here. So private channel data queue. So public producer. So here this dot queue equal to queue. So after that, the run. This is implemented. So delete date message here. So while true, nap for a while and sleep utilities dot nap. So it will temporarily wait for that. After that, we have message equal to new date and system.out.println the producer produce plus message. So the message will be displayed. You just have the glance of this here, because in detail we cannot discuss the things. So here the another side we have the consumer. The consumer also implement the runnable. After that, here we have the public consumer. Okay, so the constructor this not queue equal to queue. So after that, again the run from a method here. So date message while true, again the same, that is nap after that message, and that will be displayed. We'll see the threading issues. So what are the possible issues in using the threads? So here we have listed so many. We'll discuss this one by one in detail now. So the first one is semantics of fork and access. The question is whether whenever one of the thread, when we have the multiple threads executing on a process, when one of the thread calls the fork, the question is whether all the threads will be duplicated in the new process or only one thread. So again, it depends on the situation. So that's why the solution for this is we have the two variants of the fork function. So in the first fork, whenever a thread calls the fork, so what happens is in the new process, it duplicates all the threads of the calling process. And the second variety is whenever a thread calls the fork, only the calling thread will be duplicated in the new process. Okay. So the same thing is true for exec again. So when a new process is created, whether that during the execution of that process, whether the old process will continue its execution or it will be moved to the waiting state. Again, both the options are available. So this is the first issue. The second one is thread cancellation. So thread cancellation is the process of terminating a thread before it has finished. So it's abnormal termination. Okay. So again, to implement this, there are two approaches. The first one is asynchronous cancellation, and second one is the deferred cancellation. In asynchronous cancellation, the threads will be it terminates the target thread immediately. Okay, so immediately whenever you want to cancel, it will be cancelled immediately. But here, in case of default cancellation, it allows the target thread to periodically check whether it should be cancelled. So this is the second one, that is thread cancellation. The third issue is regarding signal handling. So we know that the signals are used in Unix system in order to notify the occurrence of a particular event. So here the signal handler is used for the process signal. So we know that whenever a particular signal is generated, the default signal handler will be there. This will be having some code that is to be executed when the corresponding signal is generated. Along with this, the user can have their own signal handlers corresponding to the different signals. The signal is generated for a particular event, the signal is delivered to a process, and the signal is handled. The options are deliver the signal to the thread to which the signal applies, deliver the signal to every thread in the process, deliver the signal to certain threads in the process, and assign a specific thread to receive all signals for the process. So that's what here. Because here till now we are discussing about the processes, but here we have the number of threads. So when the signals are generated for a particular thread, so how exactly that is to be, or whenever a signal is generated in the process, how exactly that should be dealt with the threads. So here we have the different options given. In the first option, the signal will be delivered to all the threads. Okay, no, the first option, the signal will be delivered to the thread to which the signal applies. In the second approach, it will be delivered to all the threads. The third, it will be delivered to certain threads in the process, and it will be in the fourth one, will be having an assigned specific thread to receive the signals of the process. So the next issue is about thread pools. So thread pools means what? It's a solution actually, because we know that as per the requirement, as and when required for every task, we will be go on creating the threads, and at some time the number of threads may exceed, which will result in the performance degradation. So that's why again there should be some restriction on the number of threads that should be created, that can be created in a particular process. So that's why the option is thread pool here. So whenever a process is created, so at the same time certain number of threads will be created and all will be in the waiting state. They will be waiting for a particular work to be done. Okay, so that is nothing but a thread pool. So what are the advantages of this? So usually slightly faster to service a request with an existing thread than create a new thread, because here slightly faster, because each time you need to create a thread in the normal case, but in thread pool ready-made threads are there, they are waiting for the work. Okay, so that's why a little bit faster. The second advantage is allows the number of threads in the applications to be bound to the size of the pool. Okay, it's obvious. The next one is thread specific data. We know that whenever a new thread is created, by default it will be sharing the processes code segment, data segment, and the open files. Along with that, every thread may want to have its own specific data. It is nothing but thread specific data. So it is useful when you do not have control over the thread creation process, that is using a thread pool. After this, we have the scheduler activations. So both MS2M and two-level models require the communication to maintain the appropriate number of kernel threads allocated to the application. So between user and kernel thread, it maintains the lightweight processes. The scheduler activations provide upcalls, a communication mechanism from kernel to the thread library. So this communication allows an application to maintain the correct number of kernel threads. So that's what the scheduler activation. So scheduler activation is just a mechanism through which a communication can take place between the kernel and the thread library. Okay, so this is about the scheduler activation. So at last we have the discussion about with respect to the difference between the process and thread. Okay, so here I have listed out around 6 differences. The first one is the process is heavyweight or the resource intensive, whereas thread is a lightweight and taking lesser resources than a process. What is the reason? Because we know that whenever you create a process, so it should have its own copies of the different segments and the resources, whereas when you create a thread, it is going to share the resources and the major segments from the process. The second is process switching needs interaction with the operating system, whereas thread switching does not need to interact with operating system, because here process means it is directly under the control of operating system, but when you have the threads, the process will be creating the threads, so that's why the interaction will be there with process, not with the operating system. The third difference is in multiple processing environments, each process executes the same code but has its own memory and file resources. All threads can share same set of open files and child processes. So that is obvious. So in process, so for every process it will be having its own memory and file resources. So it will consume the much amount of resources compared to the threads. The fourth difference is if one process is blocked, then no other process can execute until the first process is unblocked. Okay, so that is we know that whenever a particular process is blocked, so other processes will also be blocked stated, they will also be not allowed for the execution, but this is not the case in thread. Okay, in threads, when one thread is blocked and waiting, so other thread will continue its task. Okay, so as a result, the response will be continue to received from the thread. The fifth difference is multiple processes without using threads use more resources, and multiple threaded processes use fewer resources. Because here, when we have the multiple number of threads, the resource sharing will take place. It is not possible when we have the multiple processes. The last difference, the multiple processes, each process operates independently of the others, but in threads, one thread can read, write, or change another thread's data. So that's what here. In short, in case of processes, the multiple processes, each process operates independently. So usually there will not be any cooperation between the processes, but in case of threads, the cooperation will be there. So one thread can read, write, or change the another thread's data. So one or the other way, the cooperation will be there between the threads. So this is about the difference between the processes and threads. Okay, so with this we complete the chapter number 4. Thank you.